Hi, my name is Morton, and today I'll be presenting our work on degradation-resilient LiDAR-Radar-Inertial Odometry. To start off the presentation, I'll give a quick overview of the motivation behind the work. So firstly, we wanted to investigate a method which enables the usage of LiDAR measurements in environments which typically pose significant challenges for this sensor. In particular, we're interested in environments which contain either geometric self-similarity or environments that contain dense fog. Now, geometric self-similarity is a feature which most commonly can be found in environments containing tunnels or other similar structures with repeating geometry. An example of such an environment is shown here on the left. And the challenge in this particular situation is that while moving along the length of the tunnel, the point cloud remains largely the same, making it very difficult to estimate motion along this direction. On the other hand, the effects of dense fog can be seen in the point cloud on the right, namely in the form of added noise and many invalid points in the measurement, just a general worsening of the quality. Secondly, we wanted this method to ensure better long-term estimation accuracy than what one can expect from a purely radar inertial method, especially when using smaller form factor low-cost sensors performing some kind of velocity-aided inertial navigation, like the one seen highlighted here in this image. Furthermore, we want to ensure that the method doesn't rely on environment-specific heuristics for detecting the degeneracy, and we want to ensure that we're not adding misleading information along the degenerate axes of a LiDAR optimization. As such, our approach utilizes a factor graph for solving a windowed optimization problem. A visualization of the factor graph can be seen here on the right, which is made of state estimate nodes containing pose, linear velocity, and bias information, connected by factors representing the added information which relates to the states of the optimization problem. In order to solve the windowed optimization problem shown here, we're integrating information from IMU sensor, LiDAR, and radar sensors and turning these into factors. These factors include a typical IMU pre-integration factor, a radar frame linear velocity factor, and LiDAR plane and line feature factors. Next, I'll go over how the measurements are handled and how the graph itself is built. So first we'll cover the IMU measurements. IMU measurements are stored in a buffer on arrival for easy access later, and they're first added to the graph upon receiving a radar measurement, at which point a new node is created in the graph and connected to the graph by an IMU pre-integration factor, as you can see here in the illustration on the right. Next, after doing so, we'll want to handle the radar. The radar sensor returns a sparse point cloud where the individual points contain information on X, Y, and Z coordinates, as well as radial speed and radar cross-section for that given point. From this point cloud, we'd like to estimate the radar frame linear velocity, and we do so by solving a ransack least squares problem. With an estimate of the radar frame linear velocity, we can construct a factor and add it to the newly created node. Note that this is a radar frame linear velocity factor, meaning that for us to relate this to the state space, we'll need to compensate for the rotating reference frame. This results in the factor connecting not only to the linear velocity, but also to the orientation and the gyro bias states in the state space of the factor graph. Finally, I'll talk about the LiDAR measurement handling. Upon receiving the measurement, first we'll need to deskew the point cloud, which is done by propagating the IMU with a constant linear and angular velocity model. Given that both the LiDAR and the radar sample at 10 Hz, we choose to deskew the LiDAR to the timestamp of the radar measurement in its collection period. This has the benefit that it allows the graph to remain compact with respect to the number of nodes. Afterwards, we extract plane and line features from the deskewed point cloud, downsample the points, and register features to a submap. The feature associations are thus used to create the feature factors, which are added to the graph at the appropriate nodes. Moving forward to the experiments. For the first experiment, we present a manual flight performed in a bicycle tunnel in Bergen, Norway. This represents the geometrically self-similar environment I mentioned earlier. As you can see in the point cloud on the right, as the drone flies through the tunnel, the raw point cloud demonstrates this degeneracy. Without additional information, it would be difficult to accurately discern the robot's motion along the tunnel. Although the radar inertial odometry doesn't suffer the same degeneracy, it's still limited in its ability to maintain accuracy during these long-term traversals. This is evident in the drift and yaw seen in the result top-down ortho visualization. On the other hand, the method with both radar and LiDAR uses the fusion of these two sensors to alleviate the challenges posed to either sensor individually. Moving on to the next experiment, we present again another manual flight with the same drone, but this time in a university corridor filled with dense fog. Same as before, the raw LiDAR point cloud shows the challenge posed by the environment, where the fog is causing much of the point cloud to be rendered basically unusable, and as such, the LiDAR inertial method struggles to get through the fog. Same as before, the radar, though not being affected by this environmental challenge, is still limited in its long-term accuracy and especially mapping capabilities. The limitation in accuracy is particularly noticeable in the drift accumulating along the vertical axis. And again, we see that the proposed method, fusing both the sensors, is able to leverage the strength of both and simultaneously mitigate their weaknesses to create a better result. That brings us to the end of this presentation. On this slide, you can find my contact information as well as a QR code to the dataset we released. Thank you for listening.